Okay, so I want to give you a quick review of equilibrium thermodynamics because John mentioned that some people might not be familiar with this. So let's say you have a gas in a box and it's embedded in a heat bath. Then the state of the molecules in the gas are given by their position and velocities. And in equilibrium, this is described by the Boltzmann distribution. So you've heard about that in John's talk yesterday, right? You can use that to estimate distributions, but here it has like a real meaning because it's like the distribution of the microstates given the external parameter. So here the external parameter is the piston. It's sort of like the volume of the gas. And this Boltzmann distribution has a factor of 1 over the temperature in it. This is the Boltzmann constant. And then here's the energy function. And this is just a way to write the partition function. You can write it as e to the beta free energy. It's more convenient. So this relates to what John said yesterday, as James pointed out, and other people pointed out probably before, like Gibbs was probably aware of that, like you mentioned. This is a maximum entropy distribution given the known quantities. So here, the known quantity is the average energy. And the entropy associated with this equilibrium distribution, this is also something that James pointed out, is just simply the Boltzmann constant times the information entropy, so the Shannon entropy of the equilibrium distribution. So you take that Boltzmann distribution, plug it into P log P, and then you get the thermodynamic entropy. And then you can define a free energy as in the energy you have available. And this is your average energy that you have in your system minus the entropic part, so minus the disorder that you can't use. So this free energy is all about how much work can you get out of the system. So in this case, with the piston, it's simple, right? The work is this 1 degree of freedom that can move this way. But you have many, many, many degrees of freedom in here, and so this can exchange heat with the environment. And so the free energy tells you how much work could you get out of the system. So it's the average energy minus the entropic part, which is the sort of unusable part of the energy. And now let's say you compress this gas, and then you want to look at the work it takes you to do that. So you start at some time t0 in equilibrium in this state, and then you push the piston in and end in this state, and you let the thing relax back to equilibrium, or you can even do it quasi-statically, so it's slow, so it never really leaves equilibrium. It's this kind of thought experiment. So you want to compare initial and final equilibrium state. So you're interested in this free energy change, which is the total change in average energy minus the total change in the entropy. And the first law of thermodynamics tells you that the average energy is the work plus the heat flowing into the system. So energy is conserved. So whatever we've put in as work plus whatever heat has flown out, and it's kind of unnatural to think about it when I compress it because then heat should be flowing out, right? So the convention is that quantities that go into the system have a positive sign. So this is kind of like the work that goes in minus the heat that goes out. Okay. So that has to be conserved. That's the total change in average energy. And so from that you get the free energy change, which is that minus the entropic change. And the second law of thermodynamics then tells you, so the second law of thermodynamics tells you that in a closed system, the entropy can not decrease. So this tells you that the work that you have to do in excess of the sort of potential you have there to do work later, right? So you push this in, you do work, then you have this free energy sitting there, so the gas can now expand and push this piston out again. That's your potential, your work potential. So the work that you do to achieve the state in excess of this equilibrium free energy change has to be non-negative. And if you look at these two equations, you see that you immediately can write this dissipation as the heat that flows out of the system plus the internal change in entropy. And so that then also has to be non-negative. And this gives you directly Landauer's principle. And I don't want to waste too much time on discussing Landauer's principle because the previous speaker has discussed it in great detail. Now, what I want to tell you about is, so far this was all equilibrium thermodynamics for biological things, but also for computing engines. To stay in equilibrium costs time, right? You can do everything quasi-statically and very efficiently, but you have to do it slow, infinitely slow. And biology doesn't usually have time to wait. So we want to look at systems that are driven away from equilibrium, and that can be, and this is important, not just somewhere near equilibrium, but anywhere, any arbitrarily far away from equilibrium. So in those systems, then the dynamics of the driven system matter. So you're no longer, letting the thing stay in equilibrium or letting it relax back to equilibrium and comparing equilibrium states. No, now it really matters like how you're doing your computation. And so you'll see that this dynamics sets a new bound in dissipation. So the bound I showed you before here comes straight from the second law of thermodynamics, right? This is one way of stating the second law of thermodynamics. This excess work has to be non-negative, so the lower bound is 0. So now I'll show you that for these systems driven far away from equilibrium, the lower bound will be what I call the non-predictive information. So it's that part of a system's memory that doesn't allow the system to make any predictions about what the environmental signal is going to do in the future. So what's the setup? You have some environmental variables that we call x of t, and you have a system with some state variables that we call s of t. And this system is embedded in a heat bath, and really a lot of assumptions go into this, like this treatment goes back to theory that has been developed over the last 20 years or so, and most notably by Gavin Crooks and Jarzynski. And so all of the assumptions that they make, I'm also making, but I don't want to discuss these details here because I don't think 30 minutes are enough. So I just want to show you sort of like an overall picture. This is the setup. The environment drives some system which is sitting in a heat bath. Now, here's an important difference to what all this theory that I developed previously is like. So in their previous theory, the environmental variables are set by the experimenter, so you have complete control over them. So they're a deterministic function, you know them. But let them be stochastic, because if we want to think about a biological system, that system would be sitting in some kind of like stochastically fluctuating group. So let the environmental variables be stochastic themselves, not just the system. I mean, obviously this is a stochastic variable, right? And then suddenly this looks a hell of a lot like a learning machine, right? So here's a sketch. We have some input data, we're sitting at some time t, and we want to use our past experiences to predict future experiences. And to do that, we're going to form some kind of summary of the past. So the summary variable S or the state variable S, they're the same thing. So if you then look at the stochastic thermodynamics of these learning machines, this is what you find. You find that, so here's the signal variables evolving in time. So this is discrete time now. Again, this makes things much simpler for me. If you could do it in continuous time, but then you have to use a master equation and so on. This is the system variables running in discrete time. And so work is being done by the environment on the system whenever this x changes. And then heat gets exchanged with the environment whenever this s changes. So if you focus just on one of these little work steps, then it's really easy to show that the non-predictive information, which is the memory that the system has about what has just happened in the environment, minus the instantaneous predictive power that the system has.
So those are mutual information?
Those are regular Shannon mutual informations, which thankfully you have introduced in your first talk. So this non-predictive information, right, this is the part of the instantaneous memory that does not allow you to make predictions. This is the predictive power. The rest of it is non-predictive clutter. And that is directly proportional to physical dissipation encountered in this little work step. Okay?
The system collects active states or
No. You want to discuss this later, or you want to discuss it now?
He's wanting to know what you're wanting to know what SOT means? Yeah, yeah.
So, you missed the beginning of the talk. Of course. All the cool people miss the beginning of every talk. Okay, so there. Instantaneous non-predictive information is the same as physical dissipation. So work that cannot be used anymore to do anything with in the future is the same as information that cannot be used to predict the future. Now,
Work sub-dis?
not in these slides, but in the paper and in many, many other slides. I didn't want to put too much detail because
Angle brackets is expectation value. Angle brackets is expectation value.
it's expectation value, yeah. So the WDIS here in this formula is actually the work done in excess of non-equilibrium free energy change. Okay? Now what you're eventually interested in is not this microscopic time local expression here, but it's like you want to sum over time, if you want to like test this in the laboratory or whatever, and then you want to have a bound on the regular dissipation, the excess work that we call it. So I'll show you this in a minute. But I just want to point out that this is a very fundamental result, which also holds, for example, for quantum systems. And in quantum systems, it's nice because it provides a new interpretation for quantum discord. So that is then the thermodynamic inefficiency of the most energetically efficient classical approximation to a quantum memory. And there is a possible, if the signal is classical, you have no quantum advantage, obviously. But if the signal is quantum, then there is a possible quantum advantage in terms of dissipation. And then we've shown recently, it was like paper in preparation or whatever, that there is also a quantum predictive advantage. But this is only for quantum processes. And we can show that for classical signals, there is no quantum advantage. It's just an aside to convince you that this result is really fundamental. Now we're going to do what I just said. We're going to like sum over time. And then when we sum over time, we pick up the heat terms for you here, right? And so then we get like an inequality, and we get a lower bound on the excess work. So this is the promised, new lower bound on this dissipation. So remember, the second law of thermodynamics tells you that there is a zero here, right? So here we have this non-predictive information instead. So obviously, like David mentioned, this means that if you observe a biological system that is highly, highly efficient, that is like 99% efficient or something like that, so that approaches this bound, then its dynamics must somehow implement this prediction. It might not be easy to read off exactly how they do it, but they have to because of this. So that's kind of cool, because that means that perhaps, we kind of pride ourselves with doing this predictive inference as scientists, like it's what we do. And perhaps nature has to do that on all levels, and that would be kind of exciting.
But again, just to clarify, the strength of that selection pressure really depends on what fraction of the total energy budget is actually going to the Landauer.
Yeah, I'm not saying it's a selection pressure. I'm saying if you observe that there is a machinery that is highly optimized for thermodynamic efficiency, right? So
That's all clear. That's all clear.
then it must be that it's doing something predictive.
Selection pressure versus sufficient statistics inside the system. But the question of how much selection pressure on the evolution of the
Well,
organism.
I really want to talk about selection pressure or evolution of fitness functions, because just like you, I have never understood these fitness functions, so I'd like to keep that out of my vocabulary, right?
Well, you can just
But so I wouldn't want to go that route. I wouldn't want to say, like David just mentioned, there has to be a fitness function and this has to be part of the fitness function. I think that might be a stretch. I don't know. Maybe not. I don't know. But clearly there is something going on here that links thermodynamic efficiency with predictive power. And so if you have a system that's super efficient, then it must be doing something smart. That's all I'm saying. Now, we can take that as a motivation for efficient computing. So rather than saying, you know, this will be the kind of like natural selection pressure. I mean, people argue about this. People argue about, like, do neurons approach the Landauer limit or not, right? Neurons seem to have some aspects of them that are highly optimized and other aspects that are very wasteful. So I don't know how useful this route is.
Terrible liars.
Yeah. So instead of doing that, what we can do is we can take this physical approach as a motivation for us machine learning dweebs to think about efficient computation, right? We can view the system state as a summary of the environmental states that it has seen in the past. And then we can interpret this information that it shares with the past as the bit cost. And we can interpret the information it shares with the future as predictive power. And then we have an optimization problem. We want to minimize the lower bound on dissipation at fixed predictive power. Well, we have to minimize the bit cost. So I want to take you through this to sort of motivate the bottleneck, which is, you know, my task to explain in the next 10 minutes. Okay, so here it goes. There's a basic challenge in communication and data modeling, and that has to do with making abstractions. You often want to represent a signal not exactly, but you want to represent the relevant or sort of the important aspects of a signal. So you want to process this information. You can view this as a coarse graining, clustering, abstraction, what have you. And you want to do this in a meaningful way. You also want to do it in an efficient way. So let's go back to our original train of thought. We have this past experiences that we want to map onto some kind of summary to predict the future experiences. And there is a map which can be, in general, stochastic from the past to the summary variable. That's this map. And so optimal maps would have to fulfill the following optimization problem here. So don't worry too much about the math if you're uncomfortable with it. I will take you through it a couple of slides down the road. I just want to point out here that if you look at the family of optimal solutions, you see again that it's this shape with this Boltzmann factor and the DKL here. So it's some kind of distributional clustering. And this alpha variable here sets the trade-off between predictive power and bit cost. So it's like a Lagrange multiplier. And as that goes to infinity, so that's a typo, as that goes to infinity, what you rediscover is the causal state partition. And so there you have your sufficient statistics. Okay. All right, so now let's take this as a motivation for, this really is an instantiation of the information bottleneck method, but in general, you don't have to confine yourself to summarizing the past to predict the future. You can just, you know, summarize or cluster anything to keep information about something else of interest. So the information bottleneck method treats this problem, right? It says, let's say you're given co-occurrence statistics of two things. This is your data which you have, which you want to summarize. And then this is a relevant variable. And you're given the co-occurrence statistics of these two things. So there is a mutual information that these two things share. Okay? Now what you wish to do is you wish to construct a summary of this x variable in such a way that you minimize the bit cost while keeping as much relevant information as possible. Okay? Simple. Again, same story as before. You get these optimal solutions that look of this type, and then here you see how this is distributional clustering, right? Because it like lumps together all the data points that induce the same or similar distributions over the relevant variable into the same cluster. Okay, so now the solutions here, this is just a formal solution, so you have to find them iteratively by iterating these three objects, these four objects actually. So there's an iterative algorithm that does that for you. And this method is useful for clustering, and it's been very successful in document classification. remember how I said that you have to be given the co-occurrence statistics? Well, what about learning? I mean, like in learning, you don't know the distribution you want to estimate it, right? So if you estimate the co-occurrence statistics, then that estimate is subject to finite sample errors. And so you have an overestimate in relevant information which you need to correct for, and this correction will give you some kind of complexity control. And so you can talk about learning in this framework too.
By complexity control, it's sort of like
Stop you from overfitting. So for example, you won't use too many clusters to describe something. Okay, so now how does it relate to rate distortion theory? I'm going to talk about that. Thermodynamic work, cool stuff. I want to talk about it, but I might be running out of time. Max End, catch me at lunch. Cluster analysis, same thing. And then I also have a generalization of the stuff from which you can derive all this other stuff as special cases, and I put it in the slides so you can look at them and then talk to me. This won't be enough time to discuss it, I don't think. So rate distortion theory, the basic idea, I think, that Shannon's discussing in his paper was that a continuous signal really has an infinite information rate, but you don't need infinite accuracy for any reasonable application. You can deal with some level of distortion. So you don't need like infinite fidelity. And so the question then really becomes is what is the information rate of a source given that fixed level of distortion? And so he defined this information rate in this way. It's the smallest rate you can achieve if you vary the representation. When the source is given, you can vary the encoding and the decoding scheme, right? So it's the smallest achievable rate under a fixed level of distortion that you are willing to encounter. Now,
expected distortion.
yeah.
I guess I've seen some older versions or something where they have like an upper bound on distortion.
Well, this is what actually appears in Shannon's original paper. But then since then, there's been a lot of work on this, right? Because the coding guys are interested in blocks of symbols and making deterministic codes and producing them. So they're interested in slightly different questions. I mean, here what I'm going to show you in the next slide is just simply that the achievable, you can compute the rate distortion curve, and it just gives you, it just delineates the achievable from the infeasible region. So you have a line here on which these optimal models lie, and you know that you can't do better than that. That's all. But the coding guys, they're interested in actually making code. So, yeah. Now, if you want, I can take you through this math, or I can go on and try to talk to you a little bit about this thermodynamic stuff more. What do you want? Okay. Now, the information bottleneck is quite obviously a special case of rate distortion theory, which you get if you plug in this particular distortion function. That's the Kullback-Leibler distance or relative entropy between the distribution over the relevant variable given the original data compared to distribution of the relevant variable given your summary of the original data. Okay, now thermodynamic foundations for this. So again, there's a lot of detail here which I'm going to skip. But let's say we're running a memory and we're using this memory or this measurement to extract work out of a system. So X is going to be our work medium, our system that we can extract something out of. Y is going to be our memory. We start in a state where the joint distribution factorizes, so they're not correlated. So Y is in this Y0 state, and I'm giving this the Q of Y here instead of P of Y, because I want P of Y to just simply denote the marginal of the joint distribution after I have correlated them. Now I'm going to change this Y guy in such a way that it correlates to the X guy. I have to presumably put in some work to do this and probably dissipate some heat. In the next, so I've now correlated this. It's taken me some effort to do so, but I get something out of it. I get a potential to extract some work out of this thing. So Szilard's engine is a perfect example of this, right? I measure on which side of the engine the particle is sitting. I have put in my partition. When I know where the particle is sitting, I can extract work from it by moving the partition in the right way. Okay? So this is what I'm doing in the next step. I'm extracting work presumably, there's heat flowing again. And then eventually, to get like a cyclic process, I have to reset both things back to the original. Okay? So now I'm going to ask, what is the total effort of running the memory Y? And what is the total maximum work potential that I can have by extracting stuff from the system X? So the work I have to do on Y is upper bound again using the second law of thermodynamics, right? Oh, sorry, it's lower bound. That's again a typo. By the free energy changes involved in the two manipulations I do, this one and the reset. And that turns out to be dysfunctional. It's the average non-equilibrium free energy of the conditional distribution of Y given X averaged over all X minus the non-equilibrium free energy of P of Y. And for the maximum work extraction potential, there's probably another typo here, it's the other way around, basically. And so because I'm taking into account the reset, these initial and final state distributions, which can be arbitrary, disappear. And I'm only really looking at this distribution and its marginals. And so you see basically immediately that if you assume that the average energy does not change, then you get this relation. The difference, so actually then the least effort you have to put in to run your memory equals the maximum work potential you could get out of your work medium. Let's just call it delta F because it's the same thing. And that's directly proportional to the mutual information. So mutual information is related to change in free energy, which in turn has to do with work, right? The work I have to put in to correlate these things, the work I can pull out using these correlations. And this really lends a thermodynamic foundation to Shannon's approach. So now we can grind through it, right? We have rate distortion theory. Let's postulate a least effort principle. For a given quality of reproduction, I want to minimize my physical effort because I'm lazy, right? Like that's what nature is, right? Lazy. Nobody finds this funny. Toby Berger got really upset about that. So you have a laziness principle, and that, because this is KTI, is exactly the same as the rate function, apart from the KT, which is just the units, right? So you have that the optimal lazy representation lies on the rate distortion curve. So there's a direct motivation for using Shannon's mutual information as a measure of bit cost, because really it is a thermodynamic cost. It's the least effort that you would have to put in to correlate this Y, to run your memory, this Y thing. In the same way, you can look at his channel capacity. Now, for the channel capacity, you're given the statistics of the encoding and the channel and everything that's fixed. And all you can do is search for a source that's more or less matched to your channel. And so here you can say, well, I want to maximize the extractable work. I want to maximize my work potential, right? And that is directly proportional, because this is KTI, to the channel capacity as defined by Shannon. So again, it lends a thermodynamic motivation to what he defined. Next thing is information bottleneck method. Now that thing is a bit more complicated. You have your relevant variables, so you basically have two systems, one of which you will measure and one from which you will extract work. And basically the motivation here is you want to find a minimum effort representation of this system that you're measuring, such that you can extract the maximum possible work from the other system. So the IB is kind of an optimally lazy maximum work extraction method. Okay, now I think I'm done, because it's 11:30 on the nose. And if you're interested, there's ways in which you can generalize this to dynamical and interactive learning, because animals and embodied systems really like interact with their environment. They can change to a certain degree the things that they're trying to predict. So for any real system, you have to take that into account. And the learning is dynamical, and decisions are made under uncertainty, et cetera, et cetera, et cetera. Right, thanks.